How's it going, guys? This is Mr. Leon here for today. I'm going to be doing a quick review and overview over acids and bases from chapter 15 from the Chang book. Make sure you are taking notes because I'm going to be assigning these as your notes moving forward. And you will be doing these problems with me as I kind of go over some of these items. And so that needs to go into your notebook, specifically in your lecture notes. Okay. All right. So today's topic is going to be about acids and bases. And acids and bases are something that I think is very important to learn because acids and bases have a lot of different reactions that are encountered in aqueous solutions. And so most of the substances that you're going to find, for example, in this cave here, has to do with the formation of these acids, and over time they begin to build up into these different very interesting structures underneath the water. You also have things like these Alka-Seltzer tablets, or antacids, what they call them, where if you have an upset stomach, you can go ahead and put that in there and it will neutralize that acid. So there's actually a lot around us. Now, this is actually an extension from an earlier chapter which quickly defines the idea of acids and bases, but make sure you're aware that this is actually going to cover several chapters because there's actually a lot of concepts embedded. All right, so let's get a quick definition of what acids and bases are real fast. So the first thing is acids generally have a sour taste. And the common one is going to be vinegar or acetic acid, a very weak acid that is currently found in foods. Citric acid also contains citric acid, which is another common one found in lemons and oranges and whatnot. You also have a very important product for acids that they always produce a hydrogen gas when reacted with metals. This has a lot to do with the metals that are reactive as well. So for example, magnesium is a great example of an acid and a base reacting with a hydrogen gas, which you can eventually collect and have. The other thing with acids, they react with carbonates and bicarbonates, and usually this produces carbon dioxide gas. So a very common type of problem would be is how do you produce these type of gases? And again, the reason why it's important to know is because if you know, like for example, a very strong acid like HCl, you throw in a carbonate like calcium carbonate in there, you can automatically generate some carbon dioxide. And that's actually lends itself to a lot of questions about the impact of the increased number of CO2 in the atmosphere, and I can have a whole discussion about that regarding global warming. Bases, on the other hand, are the opposite, and so they generally have a better taste. So the great example is soap, and they actually feel slippery. In fact, if you actually touch sodium hydroxide that is not in a soap form, which is also commonly called lye, it actually feels really slippery. And most, I'd say, majority of the soaps contain some form of base. Okay, so this one we don't really have to know too much for the advanced placement portion, but I think it's just good to know anyway that on an arenous acid you produce the hydronium ion, and in base you produce the hydroxide. And so we'll kind of skip through this real quick. Okay, so this is the part where it gets very confusing, but at the same time important, is that there's actually multiple definitions of what an acid or base is. And the Bronsted acid is considered to be a proton donor, and a Bronsted base is considered to be a proton acceptor. So in this specific case, I have NH3 and H2O. In order to classify it as an acid, one of these has to donate into the other one. And so in this specific case, you see that the H2O is acting as the acid as it becomes the actual hydroxide. Here it's actually missing that. While on the NH3 it accepts that, that becomes the Bronsted base. So here's your acid, there's your base, and this is your acid, and now that's your base. Now on the other side of the equilibrium equation, you end up with a situation where the acid actually comes out from the base. So it's usually the opposite, and we like to call those the conjugates. So the conjugate acid and the conjugate base is usually going to be those that are resulting as of this proton donation. So for example, if you see right here this H2O, it turned into this hydroxide, it now becomes a conjugate base, while your base becomes your conjugate acid. Okay. So, all right, some properties of acid base. So this is a very classic example of what happens in water. So water undergoes a pretty much an equation that results in the H plus and the OH hydroxide being produced. And water, as you all know, is amphoteric, which means it can act as an acid and acid base, but it produces this concentration of your H plus and OH minus. This is actually called the autoionization of water. And the reason why water is used as a main solvent is because of this idea that it tends to react really well with a lot of different chemicals and compounds. The autoionization of water pretty much refers to this idea that if you have an H2O molecule, you're going to end up losing one of those H's to a hydroxide. And so in this specific structure, you can kind of see that the excess positive charge is caused by the addition of that hydrogen ion that's formed from the water, forming your hydronium. And then your hydroxide is formed from that loss of that one. So you pretty much have a positive and a negative charge here that creates that ionization. So again, the word ionization means breaking apart into its respective charged atoms. Now, what ends up happening here is if you get two water molecules, and there's obviously going to be two lone pairs here for oxygen, one of those is going to jump over, and then you're going to end up having this situation. So just keeping in mind a little bit on those dot structures. So the idea here is if you got two water molecules, one of those is going to pop over one of the H's, you're going to get the hydronium, and then the other one's going to end up with the hydroxide. Now this is actually a reverse equilibrium equation, so it's actually definitely reversible. So you're getting some water, and then you're getting some H2O and OH minus in the process as well. In this specific case, we would consider one of them to be the acid and then the other one to be your conjugate base, because in this specific case you get the acid, which is going to be turning into the conjugate, and your base is going to be turning into your conjugate acid. So although these water molecules are technically identical, the fact that they interact with each other and move that H, you end up getting those two. Alright, so let's talk about the ion product for water. So the ion product for water basically undergoes the breakdown from its water into its H plus and OH minus. And what you end up here is called your Kc. So if you see a Kc there, what you're really referring to is this idea of the autoionization of water. So what you're going to do is multiply your hydronium concentration times your hydroxide divided by the concentration of water, and that's going to tell you a Kc value. Now there's no units for this one because you're actually dealing with molarity. And K is pretty much like a reference point for taking a look at dissociation ionization abilities, and this idea that you need to break down these molecules into different pieces. So H2O is going to be a constant in this specific case, so we're going to keep that number down. And what we're going to do is go ahead and see if we can solve for K, what they call Kw. So if this is a constant for H2O, and then that's going to equal to Kw, so Kw should equal to the multiplication of the H plus and the OH minus. This is called the ion product constant, or Kw. And what that basically means is that if you multiply the concentrations of your H plus times the concentrations of your H minus, you should get a constant, which is Kw, or also equal to Kc H2O. Okay, now this is actually a very, very common one. That's the reason why we end up getting the pH of 4 all the way from 1 to 14 on the logarithmic scale, because this actually tells you what that concentration is going to be at a specific temperature. Now in this specific case, it's going to be at 25 degrees Celsius. Obviously that will change if the temperatures rise or drop. So keep that in mind, that as you're doing this, that you always keep in mind that it's actually at 25. Now the answer for Kw is 1.0 times 10 to the negative 14. So that basically says that in an aqueous solution for anything that you're putting into water, you're going to definitely have this balance of pH. And so obviously if that hydronium or hydroxide concentration shifts, you should be able to get a total of 1 times 10 to the negative 14. In this specific case, we know that the equal amounts of hydronium and OH concentrations are the same. And so in this specific case, the solution is going to be neutral, aka water, which has a pH of 7. Because the OH and the H plus are equal, water has that specific case. However, if you increase this to an H plus, which means it's greater than OH minus, in this specific case, the solution is going to be acidic. And your third one is when you end up having the opposite, and you already guessed it. What would it be? Yes, it's going to be basic because the OH minus is going to be in. So when you're looking at a KW equation, what you're really looking for is basically this idea of figuring out what the H plus is and what the OH minus is, because you already have the total. So some simple problems that can go about it is that if I give you the OH minus, can you solve for the H plus using that? And the answer is yes, by doing some simple division and multiplication. All right, so let's do a couple of sample problems. So go ahead on your notebook, go ahead and write these down right now, as I'm going to start asking you guys some questions. I'll give you, you can pause the video here so that you can go ahead and see if you can complete this correct answer. So the question reads is, what is the concentration of OH minus ions in an HCl solution whose hydrogen ion concentration is 1.3 molar? So in this specific case, it's a very clear-cut question about using this idea of your concentrations from OH and also from your H plus. And because we're only given one number, we're definitely going to have to use something that has a constant to figure out the other one. And so let's take a look at the first part. So we're going to be using our KW. So on a KW, you're always going to have this as a total value for anything, regardless of what the solution is. It does not have to be just water. So in this specific case, you're going to get something like hydrochloric acid, and you want to figure out how much of the OH minus is in there. So if you know it's a 1.3 molar of HCl, which is a very strong acid, what you're going to do is that you're going to use the 1.0 times 10 to the negative 14, and then you're going to put in whatever you know. In this case, your H plus, so 1.3 molar. And then you're going to reverse that reaction, getting OH minus equals to KW over H plus. In this specific case, you're going to get 1 times 10 to the negative 14 divided by 1.3. In this specific case, you're going to get a concentration of 7.7 times 10 to the negative 15 molar. So this is actually kind of interesting, because if you take a look at HCl, you're like saying, well, how is it possible that you don't have any hydroxides? Well, what happens is that when you dump this in water, okay, you're going to definitely get these hydroxides coming in. And so the number of hydroxide ions for this specific one is actually very, very small. But nevertheless, it's actually right there. It's actually 7.7 times 10 to the negative 15, which is a very tiny one. This actually makes sense because a 1.3 molar solution of hydrochloric acid is actually a very, very pretty concentrated acid. All right, let's take a look at the next one called pH, a measure of acidity. So you may have recalled that the pH is going to equal to the negative log of the concentration of hydronium ions. So the reason why we use log is because we don't want to deal with these very large numbers, and pH kind of gives us a really nice value to kind of say, okay, if I have a pH of 2, a pH of 3, what does that really mean? And this is in the order of a base 10. So every single time you're moving the actual pH scale from like a 1 or 2, you're actually increasing it by a 10-fold amount. And so what you're looking for is, if you're taking a look at the pH of any substance, you're looking to see if it's going to be neutral. And again, if it's going to be neutral, you're going to have an H plus to an OH minus concentration. And at 25 degrees Celsius, you should get your H plus at 1 times 10 to the negative 7. And that's going to give you a pH of 7. In this specific case, it's going to be a neutral compound. Now, if you look at an acidic, you're going to get a greater value of your H plus, in which case you're going to get a 1 times 10 to the negative 7, so your pH should be less than 7. I think that's pretty common knowledge. And then your basic, it's going to be the same, except that we're flipping these numbers down, where you're going to have a number from greater than 7, but obviously below 14. Now, in terms of your pH scale, obviously you're taking a look at the number of hydrogen ions that are floating in there that would determine the concentration of that substance and would indicate whether that solution is acidic or basic. All right, so here's some good examples of pHs of common fluids, and specifically this actually has a lot to do with items that you've seen. And so for the example here is going to be gastric juice or hydrochloric acid. This is actually found in a pH value between 1 and 2. And whenever you're eating or whenever digesting food, what that involves with is a set of information, a set of food that gets digested and then churns and eventually goes to your intestines. Lemon juice is a 2.4, pretty high, but then again, as you start getting a little bit higher to water, you begin to see that pure water and blood actually are at the neutral point, and then you get tears, and then milk of magnesia, and then household ammonia, which is 11.4. Now, conversely, what you end up having is this situation where you have the opposite, the pOH values. And on the pOH values, you're going to also use the same thing, where you're going to be multiplying that to figure out what the kW is. So in this specific example, going through the math a little bit, you can kind of see that you have a secondary equation that you can derive, which is going to be the pH plus the pOH equals to 14. So if I give you something like the pH and I give you the 14 value, you can always find out what the pOH is and then reverse that to find the concentration. So this is another equation that can be used in problems where they give you a pH value, and then you got to figure out the pOH. Okay, all right, let's do this last question, this last problem here. So it reads, the pH of rainwater collected in a certain region of the northeastern United States on a particular day was 4.82. What is the H plus ion concentration of the rainwater? Okay, now here is a great example of something where we're looking at, again, using that idea of the auto-ionization constant for water. So take a moment right now, you can pause the video and go ahead and see if you can crank this problem out. Okay, so here we go for this one. So we're going to look through what we're given. We're giving the 4.82, which was the pH value, and then we're looking for the H plus concentration. So we have to figure out an equation that would best fit this. And the best thing example is going to be our log equation, which equals to the pH equals to the negative log of H plus. So if you take a look at this, you can see that if you put in the H negative pH on there, you can automatically get it's like a reverse reaction where you're going to end up getting the concentration for H plus. So we're going to put 10 to the negative 4.82, and you should get 1.5 times 10 to the negative 5. Now, similarly, if you take a look at the second equation and for the OH concentrations, now we're working off something very similar. In this specific case, I give you the pH plus the pOH equals to 14. Obviously, we're going to do a couple of simple math here. Since we already have one of the values, we're going to get the pOH. We're going to go ahead and take the log of that. So if you take the log of the OH, which is going to be this portion right here, you should end up with the pOH value of the negative log of 2.5 times 10 to the negative 7. And in this specific case, when you subtract it by 14, you should get that number. So your pOH was 6.60, which was pretty much this calculation. You're going to plug it back in here, and you're going to get your 14 minus 6, so your answer is 7.40. Alright guys, well this concludes the first part of the acid base, and be sure to do the practice problems as I assigned. Thank you.